This video is about Pythagorean identities and how they relate to parametric equations. So if you see parametric equations using trigonometric functions, oftentimes we will be able to use the Pythagorean identities like sine squared plus cosine squared equals 1 in order to convert things into rectangular form pretty easily, and then you'll be able to see what usually ends up being a conic section. So if you see x equals 4 cosine theta and y equals 4 sine theta, what you can do is you can solve for sine squared and cosine squared and then substitute them into the Pythagorean identity. So if you see x equals 4 cosine theta and y equals 4 sine theta, we do some manipulation to get the cosine and sine by themselves. Then we square them, and then we replace these things into cosine squared plus sine squared. So what we end up with here is x squared plus y squared equals 16, which is a circle. So those parametric equations end up giving us a circle with radius 4. And then we can sketch the graph on 0 to 2 pi, and you can just figure out what's happening if you substitute in t equals 0, for example. You get the point 4, 0. And then if you substitute in t equals pi halves, you end up getting the point 0, 4. So you can recognize that this circle has an orientation which starts here and goes in this direction. So it's kind of important to label your starting point and then label how it's oriented the way that it travels. We can also, let's say I change the problem slightly. If I sketch the graph only from 0 to pi, I would start here and I would end up with only half of a circle. So there's a lot of different ways that you can do this based on what your parameters are, of course. Here are some more examples. So if I see x equals 3 cosine t and y equals 2 sine t, I can do the same thing, getting cosine squared and sine squared by themselves, and then substituting them into the Pythagorean identity cosine squared plus sine squared equals 1, and I end up with x squared over 9 plus y squared over 4 equals 1. That ends up being an ellipse. And likewise, I would have a similar one over here where I solved for sine squared and cosine squared, and I end up getting x squared over 4 and y squared over 9. So both these are ellipses. This is an ellipse with x radius 3 and y radius 2. Over here, I have the x radius 2 and the y radius 3. So I end up with these these ellipses. Now the question is, where is my starting point and what is my orientation? So if I substitute in 0, I see that I get 3, 0 as my starting point in this one. And if I substitute in something that's relatively easy like pi halves, I would see that I get 0, 2. So my starting point is over here, and my orientation around the ellipse goes counterclockwise. Now in the second problem, if I substitute in 0, what I end up getting is 0, 3. So notice that this is my starting point at t equals 0 here. Then my orientation, if I substitute in pi halves, I would end up getting 2, 0. So my orientation in this case ends up being clockwise. So it does matter whether the sine or the cosine is with X or Y in terms of where things start and where the orientations are. You can apply the same ideas if parametric equations have tangent, secant, cotangent, and cosecant. Mm-hmm. So we would use the Pythagorean identity, and as we've talked about in previous units, you can divide everything by cosine squared to get this. You can divide everything by sine squared to get this. And then I solve them in green to have them equal 1, because it's a little bit easier when they're equal to 1. So as you can see, these two problems, I would solve for secant squared and tangent squared. I would solve for cotangent squared and cosecant squared, and then I would substitute them into the formulas. So as I substitute these things into the formulas, I end up getting actually the exact same hyperbola. So these things, if we have a minus on the inside, I end up with a hyperbola. Now, we want to start talking about the orientation and the starting point. So if I think about where this will start, for letter A, I'd want to substitute in 0. So if I substitute 0 in, I get, well, tangent of 0 is 0, and secant of 0 is 1, so I get 0, 4. So this is my starting spot. And then if I substitute in, let's say, pi fourths, I know that tangent of pi fourths is 1, so I would have x equals 2, and secant of pi fourths is root 2 over 2, so it's going to be something else moving in the positive direction. So my orientation is moving up. So it starts in the middle, moves up, and then it goes off to infinity at pi halves. And then we start again down here, moving this way until we get to pi, and then it moves in this direction, and then it will come up here and then finish going this way back to 2 pi. So that's my orientation. So it starts here, and then down, and then back up. For this one, when I substitute in 0, what I end up getting is infinity. So I can't really label my starting point here. So what I have to do is I have to figure out where I'm going. And it's easy to plug in pi fourths and pi halves to kind of see what's going on. So if I plug in pi fourths, cotangent ends up being 1. So I'm at x equals 2. And cosecant ends up being a positive number. It's root 2. I'm sorry, I said root 2 over 2 over here, but it's just root 2. So what I end up with is 2, for root 2. So I'm at this spot, and then when I substitute in pi halves, I end up at 0, 4. So I start all the way up here, way off at infinity, and then move in this direction. So this is my orientation. And then at pi, it goes off to infinity up here. And I don't have anything down here because of my bounds. Now, if I did the same bounds on this one, what I would end up with, and I'll just highlight it, I would start here, go off to infinity. That didn't look so good. Go off to infinity. And then I would be down here, moving up and stopping here when it's done. So that's something that's kind of important to understand, is that you actually have to actually know what your bounds are if this is going to work out. Now, what would happen if I changed this problem. So notice that there's a question here. What happens if you switch tangent and secant and cotangent and cosecant? So if I switch the secant and the tangent, the cosecant and the cotangent, then this x becomes the first part and the y becomes the second part. And so I end up with a hyperbola that instead of going up and down, now goes left and right. So that means that you have to remember your Honors Algebra 2 trig when you're doing this sort of thing. And again, let's talk about orientation. Here's my start. Then it goes this way and up, and then like this. Here, I start off at positive infinity, and then at pi halves, I'm here, so I'm moving in this direction. So you have to actually kind of understand what happens, and if you don't, then you substitute in some values for t to figure out where you are. Find the rectangular equations and sketch each graph here. So hopefully by now, we have a pretty decent idea of how to solve for sine squared and cosine squared and square everything. But notice that we have some negatives, so we have to make sure that when we substitute things in, we're understanding what's happening. So when I substitute in 0, notice I get 0, 2. So I start here. And then as I move to pi halves, I would end up at negative 5. So this is my orientation. And it goes all the way until here. So notice what's going on is that since it only goes from 0 to pi, I really don't want this back half of the graph. So it's just this part of the ellipse. Likewise for letter B, if I substitute in 0, I end up getting negative 1, 0 as my initial point. And so my starting point is here. And then when I substitute in pi halves, I get 0, 2. So this has a clockwise orientation rather than a counterclockwise orientation. And it's usually pretty easy to tell what kind of orientation you have if you just do a little bit of work with it. So we're only getting 1/4 of that ellipse. Now let's define a set of parametric equations for each of these three things. And actually, we're going to do 2 of them for each, but it is important to notice that the first 2 are going counterclockwise and the third one is going clockwise. So I've set up a couple. If I have cosine t, 3 sine t for the first 2, I can start this one at 0 because that'll get me at 1, 0. And then at pi halves, it would get me to 0, 3, and so on. This one, I could start it at pi halves, get to pi, and then 3 pi halves. So notice that that works for both of those. This parameterization ends up working for both. Now, if I want a clockwise orientation, I can't use cosine comma sine. I have to use sine comma cosine, or I have to throw in some negatives. And so you can kind of just play around with it to see what happens. But if I start by substituting in 0, I end up at 0, 3. Then when I substitute in pi halves, I would get 1, 0. So that would put me here, and then all the way down to when I get to pi. I also have several other ways that I can write each of these. So I put in some negative signs and just messed around with the t values and figured out, oh, if I substitute in negative pi halves, I'm going to start here. And then as I move forward to pi halves, this graph would move in a counterclockwise direction until I get to the end. But that's just a matter of substituting some things in, and you can figure those things out on your own if we ask you to. Finally, let's do a set of parametric equations and bounds on these circles. So if I have a circle of radius 5, and it's only supposed to be graphed in the first and fourth quadrants, and it's supposed to be clockwise, I can put the sine first with x and the cosine with the y, and then that will move me in a clockwise direction. So if I substitute in 0, notice I'm going to get 0, 5. And then as I substitute in values moving toward pi, that's going to move me clockwise around the circle, and it would only take up the first through the first and fourth quadrants. So this meets the criteria that it asks me to. Now, if I'm asked to only graph something in the third quadrant, I have a variety of different ways I can do that. I can use some negatives, but I just decided to use cosine and sine for x and y and start my bounds at pi. So if I substitute pi in, I would end up at -5, 0. And then I'm asked to graph counterclockwise. So if I go to 3 pi halves over here, that would get me at 0, -5.